And we'll get into the reason why we want to ignore the textbook's redox questions. Ultimately, it's because the questions that they present are so difficult and poorly organized that to actually learn how to balance those appropriately takes way too much time out of the actual system. All right? So to go through and balance most redox reactions, what we want to look at first is kind of the trivial ones. So we've got two examples of things that might appear trivial. So for that first equation, we can go through and balance that like we would normally. Okay? Evaluate your atoms first. So how many zinc atoms do we have as reactant and as product? 1. How many hydrogen atoms? 1 and 2. So our hydrogen is not balanced. How do we fix that? We need to make our left side a 2. To do that, put a 2 out front. Why do we not put a subscript? Subscript changes the formula. Okay? So what we'd be doing is changing the entire reaction. The whole point of balancing a reaction or an equation is to balance the parts that you have. If you go through and change the parts, you're now looking at an entirely new reaction, which means an entirely new question. When you're balancing the equation, you're only changing the number of parts that go into it. Okay? So we could now go through and say that that equation is balanced. So what we went through and did it by effectively inspection, by atomic inspection, to balance everything out. Okay? One of the extra things that we need to be aware of when looking at our redox reactions is not only should we balance the atoms, we also have to balance the charge. So let's evaluate what happened with our charge. What's the charge on the reactant side of the equation? Zinc brings in 0. How much does hydrogen bring in for a charge? +1. How many hydrogens are there? What's the overall charge on the reactant side? +2. If we go through and take a look at the product side of the equation, our zinc brings in a +2 charge, and our hydrogen brings in 0. Our charge is balanced, +2 to +2. Okay? So we have two ways to confirm and verify that our equation is indeed balanced, both based on the redox chemistry and based on standard atom or atomic arrangements. What happens with the next question? If we go through and balance based on atoms, how many tins do we have? 1 and 1. How many irons? 1 and 1. So at least at a first pass through our atomic inspection, we would say absolutely that's balanced. But what happens when we check our charge? What's the charge on the reactant side? We have a +5. So we take the charge from our tin and the charge from our iron, and that, there it goes, adds to +5. What happens on our product side? We have a +6. Does our charge balance? No. So this equation has something wrong with it. Even though, based on the atomic count, we would expect it to be balanced, we don't have the electrons balanced. Electrons are a form of matter, which means we must also go back through and balance those as well. Okay? And that's where our redox reactions become trickier than our standard reactions, because we have to balance something that we can't see. Okay? So there are two approaches to how you go through and balance this. The textbook's crossover method works relatively well with simple equations. When it becomes a more difficult equation is when things become troublesome at best. Okay? So let's go through and look at their approach first. What we're going to do is look at how the electrons were transferred. So we're going to compare reactants to products and pick things that are similar. So tin +2 is most similar to what? The tin +4 is the product. Okay? They're the same element. Both of them are tins. Okay? So what changed to go from tin +2 to tin +4? Okay, it had to lose 2 electrons. So we could specify a loss of 2 electrons. Okay, why a loss? What happens if we lose negative things? We become more positive. So we are looking indeed at a loss of electrons there. What happened to our iron? Actually, sorry, back away from that. The loss of electrons means what? So what's our mnemonic device? Oil rig, or Leo says gur. Thanks for the oil rig. Leo says gur is our better one. Okay. Okay. Loss of electrons is oxidation, or an oil rig. Oxidation is loss. If we've lost electrons, we are looking at an oxidation reaction. Okay? So our tin was oxidized in this case. Okay? So if this was done properly, we would then be able to go back and find somewhere in our reaction something was reduced. So let's look at the other species. What happened to iron plus 3? Became iron plus 2. To do that, what had to happen? It had to gain how many electrons? 1 electron. So we'd be looking at a reduction. Okay, so this is something that you are hugely responsible for. You need to be able to identify these oxidation states and then compare across the reaction what changed. Did it gain? Did it lose? If it gained, reduction. If it lost, it's oxidation. You really need to know that. That's why that's been bugging me. Sorry. Let's just get rid of that. Oxidation. Now it looks a little better to me. Whoop. Okay, sorry. So, now the next part. Trying to decide on balancing. So what the textbook is saying with their crossover rule is that we'll take the coefficients from our electrons and we will make those the coefficients on the other species. So when we look at tin, it lost 2 electrons. So the coefficient on the electrons is 2. So what we need to do is put that 2 in front of the irons. And we'll put it in front of both irons. Why do we have to put it in front of both? We have to have those atoms balance out. We'll go through and take a look at what happened to the iron. The iron gained 1 electron. The coefficient there is 1. That 1 needs to show up in front of our tin atoms. Okay? That's the heart of the crossover method that they're talking about. Okay? I would argue that that is an awful method because you have no comprehension or understanding on what is actually occurring there. We'll look at that in a second. That's Mike's method. Okay? Did this actually work to balance the reaction? How many tins do we have? 1 and 1. How many irons? 2 and 2. What's the overall charge on the reactant side? We've got a +2 from our tin, and we have 2 +3s from our iron. Our overall charge on the reactant side is +8. If we shift to the products, we get a +4 from the tin and 2 +2s from our iron, and we have +8. Our charge balances. Okay? So you would be expected, this is an example problem on where you would be expected to be able to balance this one. Okay? You have to go through, evaluate how the electrons have shifted, and to go through and predict what coefficients need to go into that. As far as the question that you would get on the test, more than likely the question you would see is what is the sum of the coefficients? So what was the sum of the coefficients? 6. We add the numbers in front all to each other, and we end up with 6. Okay? There's another way that we could ask it that makes it a little bit trickier. How many electrons were transferred in the course of this reaction? Okay, how do we figure that out? So this is what I would argue this method completely destroys. You have no idea how many electrons are transferred in this reaction. One, I see with 2 electrons. In the other case, I see a 1 electron. Okay? Do we add those? Do we subtract them? Do we just say it's 2? Do we just say it's 1? Okay? It's not obvious on what's actually happening within the course of the reaction. So this is where the half reactions makes more sense. When you go through and do a redox reaction, remember, we always say redox. Why do we say redox and not just reduction? They have to both happen at the same time. So what we can do is, instead of looking at all smashed together as one reaction, split it into 2 reactions. So I look at just the reduction and just the oxidation. Okay? So what I'm going to go through and do is go ahead and split that into each of those half reactions. One of those reactions is going to involve just the tins. The other one is going to involve just the irons. Okay? Technically put on the reduction and oxidation statements a little bit early for this process, but we saw how those came in previously, so it shouldn't be that big of a deal. Okay? So now what we'll go through and do is try and balance each of these reactions on their own first. Okay? So let's take a look at our iron reaction. How many irons do we have on each side of the equation? 1 and 1. So is iron balanced? Yes. What's the charge? +3 and +2. Is our charge balanced? No. So we have to account for that charge loss. Because we are now looking at a half reaction, we can balance that charge with an extra little piece. What was that piece that's missing? What happened in the course of this reaction? Go from iron +3 to iron +2. You lost an electron. What is the mathematical symbol for loss? Minus. What is the chemical interpretation of a minus? What was that?
Well, it's an electron charge, so if you gain an electron
So that's the charge, the mathematical operation of the minus in front of our sequence. We talked about this with bond energy, and it was tricky then. You're still looking at charge. It's not a charge. If I say I lose an electron, my chemical interpretation is that that electron was a product. That is what the minus sign means. That whatever that was a product. When we look at an exothermic reaction, exothermic meant heat was released. Heat was a product. Was that energy as a product a negative value? No. The change in energy was, but the energy was a product. It was still a positive value. The difference in energy across the reaction is where we got the minus. So that minus sign is really just telling us where that term belongs. Is it a product or a reactant? So when we say we lose an electron, what are we saying? That electron is a product. How do we put that into our equation? We didn't lose an electron in that one, right? What did we do? We gained an electron. That was a lot of fun to talk about all that. We'll come back to it. Since we talked about loss, which species lost electrons, tin or iron? Tin. So if we lose electrons, what does that mean? Our electrons are products. So where would we write our electron? What's our symbol for an electron? A lowercase e. What charge is that electron? Someone said it over here. How do we specify that charge? Go to our superscript with an electron. We've now specified that an electron is a product in this. Okay. How many electrons were lost? How do we specify that 2 were lost? Put a 2 out front. Does that balance our charge? If we look at our charge on the reactant side, it's +2. If we look at the charge on our product side, +4 plus 2 times -1, and we end up with +2. So by putting the electron down as a product for our oxidation reaction, we can now balance the charge. Kind of cool. Okay, what happens to our iron? I see you. Let me finish the next statement here, and we'll come back to you.
I'm hesitating to ask, but go ahead. Yeah.
Take a look at the iron. What happened to the iron to go from +3 to +2? Gained an electron. What does that gain mean? What did loss mean? It was a product. So what does gain have to mean? Has to be a reactant. So we would write our electron on the reactant side. What charge was our electron? Negative. Do we have a way to check this and actually confirm that we put it in the right spot? Well, let's say just just for the heck of it, let's say we decided it was an electron supposed to be on the product side. Let's ignore the tin for the moment. What's the overall charge on the reactant side for our iron? What's the charge on our product side? +1. What was it before we put the electron on? Did we get closer or further from getting those charges to be the same? Further away, which means we put our electron on the wrong side of the equation. So,
Why are you writing +1 when it's a +2? And then I must be missing something.
what happened in the iron equation to go from iron +3 to iron +2? Oh, what were you saying? What's the +2 that you're talking about?
+2 is the iron next to the second iron on the
Let's finish off what you're talking about there, because yeah, you're thinking about something else.
Okay.
Plus an electron. Why did I write +1? I asked for the charge on the product side. How much does iron contribute? +2. How much does the electron contribute? -1. G equals our overall charge. The overall charge must balance on both sides. What you looked at was just the iron atom. I asked for the whole product side. Okay? So that means we have to have the electron put in as a reactant. How many electrons need to go in? Why 1? It only gains 1. How else could we attribute to why we only need 1? What's the overall charge on the reactant side now? +2. What's the charge on the product side? Do our charges balance? Yes, which means all of our coefficients are correct. Okay, so let's go back to your initial question and see. Did it come up?
Yeah, I'm
Still working on it?
lost.
Okay.
Yeah, go ahead. Maybe
So what we're doing is evaluating each of those independent reactions on their own first. Okay. The whole idea, though, is to balance our overall reaction. So how could we balance the overall? Well, what we do is add these two reactions with each other. Okay. As I add them up, though, if something shows up as a reactant and as a product, I can cancel that term out. Much the same if I wrote up the equation. Let's do this. X plus y equals y plus 0. What is x? How do you know it's 0? The y's are the same on both sides of the equation. I can subtract y from both sides, and those terms cancel. We're doing the exact same thing here, except now it doesn't completely cancel. The 1 electron as a reactant cancels with 1 of the 2 electrons as a product. Which means now when I add these two equations together, the end result, come on, there it is. We get this equation. Charges balance. Everything looks okay. Atoms match up. But we've got a problem here. That problem is that electron. When have you ever seen an electron sitting around by itself? You don't. Okay? Charges are incredibly unstable. One of the things we can do to stabilize a charge is spread that electric density over a larger surface area. Okay? Well, where is the charge for an electron? Is there anything to potentially stabilize it? If there was a proton, we wouldn't have a single electron because we'd have hydrogen. Okay? We have nothing to stabilize that electron. So the best way to envision electrons is these angry little devils that can never be by themselves. So in the course of balancing our reaction, we ended up with an electron as a product. We cannot have an electron existing on its own. It does not happen. What if we'd added it up and our electrons had been left over as a reactant? Well, if we can't ever get an electron on its own, we wouldn't be able to add it as a reactant either. Okay? So what that means is that in the course of these two reactions, we have to make sure that when we add them in such a way that the electrons completely cancel out. Okay? So that's the next issue that we... Oh, shoot. Go away. Don't see that. Okay? How can we set up our equations such that the electrons cancel out? What does the coefficient in front of our electron need to be on both sides of the equation? 2. Let's go more generically. the same. Okay? We need to get them exactly the same. Okay? And remember, when we go through and run a reaction, we only use whole number coefficients. Can I get 2 to equal 1? In general, mathematically, how do I get 2 to equal 1? Divide by 2. So I run this reaction half the amount of times. If I have one tin atom, can I get only half of that tin atom to react? No, that's not physically possible. Okay? So what I will do is adjust the smaller number. I need to make this 1 equal to a 2. How can I make that 1 equal to 2 electrons? I need to multiply it by 2. But when I multiply by 2, do I also have to multiply the iron? Where is that electron going to? It's going into the iron. If I just multiply by 2 and get 2 electrons, cool. Let's just say we do that. Here it is, 2 electrons. Is my equation balanced? It's no longer balanced. If we look at our overall charge on the reactant side, we're now down to a +1 versus a +2. So sure, we can make that a 2, but now the equation's not balanced. How would we balance the equation? We have to multiply everything in that equation by 2. And what we're saying by doing that is that we need to run that reaction, converting iron 3 to iron 2 twice. For every time I run that twice, I can get tin to convert into tin plus 4. Okay? So what we're doing is adjusting the balancing of those coefficients to make sure that our electric charge balances out, that our electron transfer balances out. When I locate that 2 all the way through, now what happens? I get 2 electrons are a reactant. Well, where did those 2 electrons come from? For them to act as a reactant, they had to come from somewhere, and we can't supply them. What supplied them? The tin. In the process of tin plus 2 converting over to tin plus 4, what does it release? 2 electrons. What do those 2 electrons then do? They then react with our iron plus 3 to convert to iron plus 2. When I now add these 2 equations together, since the electrons are the same on both sides of the equation, I can cancel them out. Now when I add the 2 equations up, there's nothing to cancel out my iron plus 3 because it doesn't show up the same on both sides, so it shows up as a reactant. And there's 2 of them. What happens with the tin? Comes down just the same. And what we end up with is now a final equation. Is that final equation balanced? Yeah, we got the exact same result as the textbook did with just swapping coefficients. But with the textbook, we couldn't tell how many electrons were transferred. How many electrons were transferred in this method? 2 electrons. And we can see that from the equations that we use to balance out. Our tin gave up 2 electrons, which were then immediately consumed by our iron plus 2 to convert, our iron plus 3 to convert to the iron plus 2. Okay? We have to have these 2 types of reactions, both the reduction and the oxidation, happening in concert so that the electrons are always consumed. They are completely removed from the reaction and we don't see them in our overall equation. Right? And that is ultimately what we're looking at when we're trying to balance our redox reactions, is make sure that we account for that balance of electric charge. Okay? So the 2 methods you can, well, there's ultimately 3 methods you could go through and use. 1, you can hope and pray that the other ions present in that reaction give you the answer, which is what we've been seeing with all the other balancing reactions. In a single replacement, how do you know that your charges balance out? You looked at the anion, the counter ion to your metals. If that balanced, then everything else balanced. If we go through in a situation like this, where I'm not giving you those anions, you can't see to use those to balance. So you have to come up with another method. You can use the textbook which is ultimately that kind of crossover method, or what you do is break it into the two individual reactions so that you can see what's actually occurring. Okay? Now, questions?
When's your next office hour?
2:30, hour and a half. Did I do that? I think I did that right.
No, I got a lab.
Yeah.
I mean, tomorrow.
Wednesday, Monday, Tuesday, Wednesday, Thursday, Friday. Guess when I have office hours? Every single one of those days.
Is that 11?
Hour and a half. Wednesdays, it's 11 to 12:30, yes.
So we can do the crossover method.
You can do the crossover method. It's the exact same thing. There is no difference whatsoever. So, well, it's easier to get the answer. Do you have any understanding on what actually happened with the chemistry? And that's the argument that I'd be making, is that with that method, you couldn't answer how many electrons were transferred.
Is that question you'd be asking?
Yeah. You need to understand what's happening with the chemistry. Okay? And in that method, ultimately all they're doing is hand waving and hoping, oh, it magically works. Okay? Which is great when it magically works. What if it doesn't? Okay? Then you're stuck and frustrated and don't like balancing reactions. Okay? The idea is, again, with this, split it into the things that are similar. When we started this, we go all the well, now it's delete. We go all the way back. Okay? How do we split the reaction? We're given an overall reaction. What's similar across those two? Tin and tin. Why'd you pick tin and tin? Because it's the same element. Why'd you pick iron and iron? It's the same element. What you're trying to do is identify things that do not change. Okay? And pick those as your simplest things to compare. So we would write out, I know you said tin first, but for some reason I started writing that. To our iron plus 2, and our tin plus 2 to our tin plus 4. All we've done is simplified. We took a long equation, and instead of turning it into this big long thing with a whole bunch of numbers, we've now turned it into two separate equations that only have two things in them. Now what we have to do is evaluate what changed. We found the most similar thing in each case to simplify our problem and make it easier to look at. Now what changed? So what I'm saying in that case is I don't care what happened to the tin. That is irrelevant. What happened to the iron? We'll look at another one. What happened to the iron? Okay. If it gains electrons, we would put our electron as a reactant. Okay? Because it had to gain. To gain something, you need to start with it. Okay? What happens in the course? Now we can try and look and balance our charge. Does our charge balance? Yeah. Okay? So our equation right now is perfectly accurate. On its own, that is a valid equation. What happens with the other one? So now I don't care what happens with the iron. I'm really not going to like erasing this. But oh well.
So you could say that if it gains an electron, it's electron in, and therefore the electron needs to go on the left-hand side. If it loses an electron, it's electron out, therefore it needs to go on the right-hand side.
Exactly right. That's all it is. So now we look at our other equation. What happened to the tin? Okay. If you don't know, guess. Okay. There's a reasonable guess. Almost everybody will start with the first. So let's say it gained electrons. What happens to the charge?
It's going to
What's the total charge on the reactant side now?
+3.
-1 plus +2 gives us a +1. A lot of people are getting confused with the addition within this. I'm perfectly all right with that. I'll screw it up all the time too. How do you fix that? Write it down. I cannot stress that enough. Write it down. I would argue thinking about it is going to get it wrong. Don't think about it. Write it down. Once it's written down, you can now look at it and evaluate it. Now is when you can think about it, because there isn't a, did I say that was a plus or did I say that was a minus? Or maybe it was supposed to be a minus for the 2. No, it was a plus for the 2, but a minus. No, none of them were minus. All of them were minus. There's too many different things that are going to change inside your head that's going to get you wrong. Don't do it in your head. Write it down. What's the charge on the product side? Plus 4. I started at a plus 2, going to a plus 4. I want those charges to be the same. I'm now at a plus 1. Did I get closer or further? Now there's a difference of 3 versus a difference of 2. That gets me further from my end goal, which means I put the electron on the wrong side. Oh well, reasonable guess, I guessed wrong. Nice thing about guessing in this case is what are your 2 options? Or sorry, how many options do you have? 2. So if you're wrong on one, you're right on the other. So check it. What happens when we put an electron now on the other side? What's the charge on our reactant? Plus 2. What's the charge on our product side? Plus 4 plus a minus 1. Well, that's a 1. What do we get? Plus 3. Am I getting closer to plus 2 or further? Closer. What was the whole goal? Get the exact same charge. Not quite there, so what do I need? I need an extra electron. Now what happens? I have my plus 4 plus, oh man, that looks ugly, sorry. Negative 1 times 2, negative 2. What's the math? Plus 2. Do my charges balance? Yes. How many of you can't see what I wrote up here? Don't understand at all what I've written as far as the mathematics?
I understand that part of
Okay.
it.
The mathematics, that's all I'm asking about. Okay. The issue that I would suggest that you're having is that you are not writing out the mathematics, which means you're trying to interpret chemistry, mathematics, and English all in one breath. In that single breath, you will mess up one of them. Any one of those get messed up, what happens to your answer? It's wrong. Convert. Write all of those individual steps out. Yeah.
The problem I have is I can't absorb fast enough. Like you lost me probably 10 minutes ago. It's because my mind can't.
So
it takes me
that
time
absorption process we fix in 2 ways. One, all of the lectures get posted online,
Right.
which means you can go back at your own time and watch those lectures. And I will tell you right now, based on the YouTube views, you're not doing it. I'm not saying you, not personally you, but the class as a whole is not taking advantage of that information.
Wow.
Okay?
It's
Which, okay, if you don't want to accept that information, then fine, you don't have to take it. Where do you have to get that information instead? In a single lecture that we're talking about in here, which would mean frantic note-taking. How many of you are not taking notes?
I'm taking notes all the time.
Well, so, but it's not, I'm not picking out any one person. What I'm saying is that that information is there, and it's your choice on what you're doing with that information. I'm on campus close to 50 hours a week. Okay? In those 50 hours, I've seen 4 of the class out of 100 students. I know I'm intimidating. But if I'm here, I can give you that help. The tutoring center, there's lots of capable tutors that can help you with that information as well. Ultimately, it's going to come down to practice, doing the problems on your own. When it comes to the test, do I walk you through the problems? No. So when you're in class and you go, yes, I understand this, that's cool. I just walked you through that problem. When you get to the test, I'm not walking you through it. Okay? You have to do it on your own, which brings up the next question. Every time we approach a problem, what do? Ask an easier question, ask an easier question, ask an easier question, until ultimately everybody has the answer. And then we go back through and make it more difficult. How many of you taking notes write down those easier questions? Okay, 1, 2. Okay, those easier questions are the questions you need to ask yourself on your own. If you aren't asking those easier questions, you're not going to be able to process the material. So it takes time and practice, and it's unfortunate. That's what has to happen with chemistry. You have to practice, and it requires lots of practice. Yeah.
Oh, I went online today, and in CGC, the Learning Center, they have a bunch of online, same thing that you're doing right now,
Yep.
for the most part.
So the tutoring center has all sorts of extra information. It's out there, it's available, there's problems for you to work. You have to work those problems. Okay? So what we can go through and do is another, because we heard a request for another problem, so let's take a look at another problem. Since I've got a couple on here. Oh geez, wow. I had to step through it really slowly. Okay? So we're going to take a look at that first one. So this is going to bring up the next important issue. I said ignore the questions in the textbook as far as balancing these go. And the reason being is that the problems they are giving you are far and away way more advanced than you will ever need to see as far as this class goes, and arguably probably more advanced than you would see in second semester general chemistry. Okay? And they give you no guidance as far as how to balance those. Okay? So let's go ahead and pick one. I'm going to pick the first one. The morning picked the third question. Anybody can quickly tell me why the third question is a bad one to pick? It's already balanced. Okay. So, cool. We could look at that one, but there's nothing to do. Okay, so let's take a look at the first one. And I might need someone to remind me, but I will try and see if I can get this in one pass. So, our first question starts with, oh geez, I think I already forgot it. Was it aluminum solid?
Yes.
Oh, cool. So we start with aluminum plus, what, chromium plus 3? Goes to chromium solid and, I didn't need to. Okay. Our textbook method has us go through and look at what changes. So what happens to our chromium? We went from a +2 to a 0, which means we had to gain 2 electrons. What happened to our aluminum? Well, if our chromium had to gain, our other one had to lose. How many electrons? 3 electrons. Okay. So the first thing that we could do is, according to the textbook, we can shuffle our numbers. Our aluminum was a loss of 3. We put the 3 in front of our chromiums. And we put the 2 in front of our aluminums. Does everything balance? Sure hope so. 6, 6. Yeah, balances out. Okay. Now the trick question. How many electrons were transferred in the course of this reaction? Okay, I heard a 5. Let's go through and check. So, to figure that out, what we do is split our reaction up. Let's try and do an understanding of what actually occurred. So let's take a look at our aluminum. Why do I pick aluminum first? It just happened to randomly be the first one there. Okay, so what happened to our aluminum? What is most similar to the aluminum in the product? Aluminum. What charge is the aluminum in the product? Okay. Any questions so far? Okay. Is that balanced? What's wrong with it? Just our aluminum. Is that balanced? It's not balanced because charge. We need to fix the charge. How do we fix the charge? We can add 3 electrons. Where do we add those 3 electrons? So 2 ways we can approach this. This was aluminum. What happened to aluminum in the course of the reaction? I know it's up in that shadow part that you can't see. Lost 3 electrons. The minus meant those 3 electrons need to be products. If you don't want to trust that, check your charge. What's the charge on the reactant side? Reactant side, our charge is 0. How do we know it's 0? Upper right-hand corner of the aluminum. What charge is there? 0. Look to the product side. What's the charge on our aluminum? What's the charge on our electron? How many electrons are there? 3. 3 plus a negative 3 gives us 0. What's the charge on our product side? 0. Does our charge balance? What does that mean? You put the electrons on the right side of the equation. Let's try that again. On the correct side of the equation. Okay? This is only half the reaction. Hence, we call it a half reaction. So let's look at the chromium. What happened to the chromium? Chromium plus 2, what's most similar to it? Our standard chromium. What happened in the course of that reaction? It had to gain 2 electrons. Questions about that 2 electrons and putting them there? Do we need to work through the balancing of the charge? Or no? Okay. If we add these 2 equations up as is, what happens? Our 2 cancels out with 2 of our electrons over there, and we end up with 1 electron as a product. Can we have electrons as a product? No. Which means, should I do this right? We have to go through and balance our electrons. The electrons produced must be the same as the electrons consumed. What is a common multiplier between 3 and 2? 6. So I need to convert that 3 into a 6. How do I do that? Multiply by 2. If I multiply the 3 by 2, what do I get? 6. Is my reaction balanced? No. What do I need to do? I need to multiply everything within that equation by 2. What happened to the chromium? How do I get 2 equal to 6? Multiply everything by 3. 2 times 3 equals 6. 1 times 3 equals 3. 1 times 3 equals 3. What happens when I add the 2 equations now? The electrons cancel, and I end up with 2 aluminum plus 3 chromium plus 2 goes to 3 chromium plus 2 aluminum plus 3. Does the equation match what we looked at earlier? Yeah, gets us the exact same answer. What's the advantage? How many electrons were transferred in the course of this reaction? 6. What answer did we hear before? 5. This allows you to see the electrons transferred. The electrons have to balance out between them. If you do not break your equations up into your half reactions, you cannot see those electrons transferred, and you have to make some assumptions. Do we still have questions on the method? Because I asked all the way through, and everybody said yes all the way through. So what's the question? You can still have questions. I'm not saying it's bad.
6 electrons. Wasn't it 3? Plus 3?
It was 3 initially. So what we ended up having,
Balance it with that 2 right there, and that's why.
what we had initially was a 3 here, and we had our 2 here. Do the electrons balance? No. So that's what,
I was thinking you did anyways.
yeah. And so that's what we ended up having to go through and do, was balance out those electrons. We did that with our iron and tin. Okay? We multiplied 1 by 2, and we multiplied the other equation by 1. So nothing changed. Okay? So the idea is to balance out those electrons to be able to see what's happening in the course of the reaction. Breaking it into the half for reactions allows you to see this. As far as the numbers of problems that you can expect to see like this, at most 1. Okay? I will ask balancing questions. You might see a full-on balancing question where it asks for the coefficients. In the case of just the coefficients, do you need to break it into the half reactions? No. You can, it's not really cheating, shortcut a lot of those steps and effectively guess at your correct answer. Okay? And it's coming from what you need to get out of the course. If this is the only class you need, heck, go ahead and take the shortcuts. Just don't get it wrong. Okay? If you need to take more chemistry, you need to be able to break things down and see those changes. Okay? Which takes time and practice. Okay? So we've now looked at 3 of the possible 5 equations that you could see as far as balancing your redox reactions. Okay? And I crossed off that last one because I don't want you to worry about that last one. Okay, as far as balancing goes. Okay? So there's two more equations there. Fish, I even told you the answer to one of them. Okay? You need to be able to go through and balance those, and it's not a bad idea to go through and figure out how many electrons were transferred. I guarantee the questions that I ask will be one of those 5. Okay? Yes, those are on the slides. Okay? Questions about that? Okay. What we're going to finish up now is Chapter 7, looking at chemical reactions. You're going to get a whole lot more practice with this next sequence when you move into lab. What type of reaction is occurring with that general format? We're looking at a double replacement. You're going to take your cations and you're going to swap their relative positions. So you're going to mix them with the other anions. So let's go through and look at an example. Aqueous barium chloride. So to start this problem off, this still seems to be a problem as well. Where do we start determining this problem? I ask for the equation. Barium chloride. That's exactly what I want to do here. Okay? I don't care what it reacts with. I don't care that there's what it's going to produce. The only thing that you need to be concerned about at the very beginning of this is what the heck is barium chloride? Because if you get that wrong, you're not going to hope to get anything else right. Okay? So simplify. Look at the individual pieces. What is the symbol for barium? What is the symbol for chloride? What's the phase? Phase? Aqueous. How do you know it's aqueous? It said. Before we advance on to the rest of the problem, we should make sure our formula is correct. Is it correct? How do you know it's not correct? Charge on barium? Charge on chloride. Does our charge balance? How do we fix that? It needs to be Cl2. Okay? That is not elemental chlorine. That is 2 chloride atoms bound to barium. Okay? It's a pretty huge difference. That 2 is there to balance the formula, and that is it. What happens in the next thing? We see reacts with. What does that mean? Plus. What's the next thing say? Potassium chromate. So we will start with K, chromate. Okay, it's a trickier one, mainly because I told you not to memorize this one, which is fine. CR04. If you don't know, what should you do? Look it up. I told you to memorize certain ones for the exam. For your homework, look it up. Which means in front of you doing your homework, you should have directly accessible, and by directly accessible I don't mean it's under some stack of paper, you should have a list of all of the polyatomic ions. The Tutor Center gives you a list. All you got to do is go in and take it from them. They're really nice about it. Okay? The other thing that you should have in front of you, how did we know barium was +2? Periodic table. So what else should be in front of you during all of your homework? Periodic table. Those 2 things and your homework and the problem where you're solving all the work down need to be directly in front of you. If they are not, you're doing yourself a disservice. Okay? Next part of this. What's the phase? Aqueous. Before we move on, what else do we need? Balance it. What's the charge on potassium? How do you know it's +1? Periodic table. Chromate. Charge. Minus is a good start. -2. Does our charge balance? +1 minus 2 gives us -1. Does our charge balance? No. Right? It's just potassium chromate. What you're doing is looking at the answer. Okay? Does our formula balance? No. What do we have to do? You need 2 potassiums. We put the 2 as a subscript. If we put it as a coefficient in front, what happens? 2 applies to everything after it up to the symbol, including the chromates. So that wouldn't help us. This now needs to produce something. Okay, so I forgot to include that word. So we produce, so there's our arrow, what? Sodium chloride? Sodium? We've got potassium as one of our metals, which needs to now pair up with chloride. Okay? I'll tell you right now, I've been seeing a lot of people do this. Why'd you put the 2 there? It's diatomic in its elemental state. Agreed. Is it in its elemental state if it's bound to potassium? No, so you can't put the 2 there. So it's not for that reason. What's the other reason you might be doing it? We see it on the reactant. Why is the 2 on our reactant? To balance the barium. Is barium there anymore? No. Why'd you put the 2 there? You had no reason to put the 2 there. Okay? Understand why you bring in individual numbers. That 2 does not belong there. Okay? Until you verify that it needs to be there. How do we verify that? You balance the formula. What is the formula, or what's our charge on potassium? How do you know that? Periodic table. What's the charge on chloride? How do you know that? Periodic table. Does our charge balance? Yes. Do we need any coefficients? No. I don't care how many chlorides there are in the reactant at this point. All I'm trying to do is predict the one product at this point, our potassium chloride. Okay? One method that you could go through to do to help you avoid that mistake is, instead of looking at how many there are of everything, name it. Our first compound was barium chloride. The second one is potassium chromate. When we do the double replacement, the metal ion needs to swap with the other anion. Okay? So we take potassium and we pair it with chloride. What's the formula for potassium? K. What's the formula for chloride? Cl. There is no 2. Okay? Use the names to help you start to predict what's happening with these. Sometimes that can help alleviate that need to include the 2. Okay? Ultimately, I think what's happening is you're trying to force it, okay, by trying to balance all at the same time. Balance your formula first. Doesn't matter where it came from. Get the formula nailed down before you start balancing the equation. What's the other product? Barium. And sorry, I am running out of space here. Chromate. What's the charge on barium? Charge on chromate? -2. Does our formula balance? Yes. Now that our formula is balanced, now we can balance the equation. Is our equation balanced? Nope. What do we need? We need a 2 in front of the potassium chloride. Now everything should balance out. Okay? Questions on that? Yes? Why did I put the 2 there? To balance. How many potassiums are a reactant? How many potassiums are a reactant? On the reactant side, there's 2 potassiums, which means on the product side, I need to have... What does that subscript mean? There are 2 potassiums. Okay? Don't worry about it. It's a very common mistake. A lot of people will make that. It's the same issue that we have with the chlorine. Okay? When we transfer it across, potassium, the symbol for potassium is K, period. The reason we have K2CrO4 is because I need 2 potassiums to balance out the chromate. The 2 is there for an entirely separate reason. Okay? So when we go to the other side of the equation, we now have to look at our formula and say there's 2 potassiums to 1 potassium. To fix that, I need to have a 2 in front of the potassium chloride. Okay? And go back and check with the other ones and verify that everything else matches, and you should see that. Okay? So the only time you will see the coefficient translate across, or sorry, the subscript, okay? Because it does happen. In fact, it happened in this problem. Where did the subscript transfer across? CrO4. Why did that 4 transfer across? That's part of the formula for chromate. When you transferred across barium, did you transfer it across as capital B and a lowercase a somewhere else? Why not? Because the symbol for barium is Ba. What is the symbol for chromate? CrO4. The 4 is as much a part of the formula of chromate as the A is part of barium. Okay? And yes, I know that's tricky because sometimes it seems to translate across, sometimes it doesn't. This is why naming the pieces can help. Okay? Next big issue with this, what is our equation missing? The phases. Okay? The phases of those products. Okay? So first off, we're running a double replacement reaction, and we could pull up those answers. Okay? And we look at the other equation. We got this. How did I know that that was barium chromate solid and potassium chloride aqueous? And then in the next one, it was sodium nitrate aqueous and lithium chloride aqueous. How did I know that? And trust me, I'm not that good. Effectively, I was told. How was I told? I looked up the rules. We're looking at something being aqueous, which means, what does aqueous mean? Dissolved in water. Said another way, what are we saying it is? It is something in water. With an S. Close. Soluble. What happens if we see an S? We see a solid. Well, there's water in this reaction. If we see a solid, what does that mean? It is not soluble in water. We have an insoluble species. So what we're looking at are solubility rules. To be able to predict double replacement reactions, you have to fall on another set of rules. Those rules are known as your solubility rules. You will be given, at very least, a condensed version of these solubility rules, okay, when it comes to the test. This is copied directly out of your textbook. So when going through and solving, predicting your double replacement reactions, you need periodic table, the question, where you're writing your answer down. I'm running out of fingers. So question, where you're writing, periodic table, polyatomic ion sheet, and now what else do you need? You need the solubility rules. All of these should be directly visible in front of you. If you have to flip back and forth in the textbook, you're spending too much time not studying. Okay? All of that information needs to be directly there. Your polyatomic ions, your periodic table, your solubility rules, then the question you're trying to answer, so your textbook, and then wherever you're trying to write your answer down. So right now we got a list of 5 different things. Never mind the fact that you might have also been answering something about single replacement reactions. And to solve a single replacement reaction, what other piece of information do you need? You need an activity series. So now we're up to 6 different things in front of you. Okay? If at any point you are attempting these problems with a nice, neat little stack of paper in front of you, you're probably doing something wrong. Or you're really that good. I'm cool with that too. Okay? I can tell you right now that when I go through and solve these, I have them all scattered out in front of me. Okay? You need to realize that information is there and you must be constantly using it. Okay? So, how do we go through and use this? Barium chromate, we said, was a solid. Okay, well, now let's give you we went back to a question mark. So we have to go back to our chart and try and interpret it. This chart is divided into 2 separate sections. The first 5 rules are your soluble rules, which mean the phase would be aqueous, AQ. The next set of rules, next 10, are insoluble, which means the phase would be solid. If it was as simple as that, it wouldn't be too bad. Notice that in our soluble one, rules 4 and 5, what do we see? Exceptions. What's the exception to being soluble? What would the answer be? Insoluble. You'd have a solid. Okay? So let's go through and take a look at this. What do we need to find? If barium chromate, we either need to find barium in our list or we need to find chromate. What do you guys find? Chromate in rule number 7. It says it is insoluble in water. The exception is rule number 1. What was rule number 1? Group 1 metals. Is barium a group 1 metal? No, which means it's insoluble, which means the phase is insoluble or solid. KCl. Again, we get to sift through the rules for either potassium ion or chloride ion. Which one do you see? Okay. I see 4. Someone mentioned 4 at least for our halide ions. It says our halide ions are in general soluble except when bound to silver, mercury, or lead. Is potassium silver, mercury, or lead? No, which means it's soluble, which means we specify aqueous. Okay. Was there another rule we could have gone to? Rule number 1, alkali metals, group 1 metals. Okay, and applying those and saying that that's aqueous. So KCl is doubly water soluble because of both rule number 1 and 4. Okay, what happens? Let's see how much information is released. Oh, not quite yet. You'll notice that I've got those first 3 boxed in. Why should I have those boxed in? Why are those different from all of the others? Which one of these things is not like the other? Right? Okay, maybe not. How many exceptions do we see for rules 1, 2, and 3? None. Okay? Which means if it has an alkali metal, it is soluble. When? Always. If it has acetate ion, what does that mean? It is soluble. Always. If it is nitrate, soluble. Always. Why would I box those in? Memorize those 3. There are no exceptions. If you memorize those, you can now shorten the amount of times you have to flip back to that solubility rule. And instead of having to flip back to the solubility rule for KCl, we go, oh, potassium, group 1, soluble, aqueous. I don't care about rule 4. Okay? So if you have those first 3 memorized, that can cut most of your work in half, if not more so. Okay? Worst case, you go through and say, okay, KCl is soluble. Well, barium chromate, I didn't memorize that. Why not? Let's call it solid. Oh, look, I was right. Okay? That guess technique will work pretty well in that case. What happens with the next one? Oh, man. Well, let's just skip to this one, because this one's a little more interesting. Okay, so let's go through and predict. What do we expect to happen? What are our metals being exchanged? Potassium and lead. Why do you guys always go to potassium? You always seem to go to the second one first. It's not a problem, I just haven't noticed that. It just seems odd. Okay, so if we go through and swap this, we're going to put potassium with what? Nitrate. What's the formula for nitrate? What's the charge on potassium? Charge on nitrate. Is my formula balanced? Yes. Go back to the reactant. What the heck is that 2 doing there? That's to balance the lead. Why do we not translate that 2 over to our product? Because lead is not there anymore. It's now potassium. Okay? What's the other product? Lead with iodide. What's the charge on iodide? -1. What's the charge on lead? This one's a little bit trickier. Okay, for our double replacements, we will assume that we will not change oxidation states, which means if I need to figure out the charge on lead in the product, that charge had better be the same as it is in the reactant. What's the charge on lead in the reactant? How do you know it's a +2? X has to be +2, which means when I go to my final answer to balance out my lead iodide, +2. Do my charges balance? Nope. How do I balance it? How do we put in the 2? Have to do the subscript directly after the iodide. We now have the formula for lead iodide. Now that we've got our formulas balanced, now we could go through and balance the overall equation. Okay? Again, this is something that you guys should be confident with, so I'm going to hopefully put the right answer down quickly. Okay? What's the phase for potassium nitrate? How do you know it's aqueous? Rule 1 and Rule 3 both say it's soluble. Lead iodide, what's its phase? It's a halide ion. Okay, remember, iodine is a halogen. If we make it negative, it becomes a halide. That is under group, or Rule 4. If we look at Rule 4, that is under our soluble category, except, what are we looking at? It's lead, and that's an exception to our soluble rule, which means it must be insoluble, has to be a solid. Okay? Your lab is going to give you lots of practice with this week. Okay? You're going to be doing lots and lots of double replacement reactions. And honestly, there's no reason to actually go to lab because all you're doing is doing stuff that you could predict right off the solubility chart. But you'll see some pretty colors. Yay, pretty colors. But everything you're doing is going off of your solubility chart. So those of you in lab right after this, make sure you have that solubility chart handy. You'll need it. Okay? Otherwise, you're going to have a very rough time of it in lab. Okay? If you need to take a picture, I guess I can wait a little bit.
That's a very good idea. Took them up there.
Jeez, everybody's got cameras, huh?
Hey man, it's the new,
The other option is there are computers in lab. You could just pull up the lecture site and download the web. Or you could look at the website on your phone too. All sorts of fun ways to do that. Okay, so we'll give you another 5 seconds. 3, 2, 1. Last reaction we're going to look at, neutralization reactions. Okay? These can get vastly more complicated, and for some really silly reason, your lab actually has you do a whole bunch more complicated ones. Make sure you talk with your lab instructor about balancing those complicated ones. Okay? Most chemists would insist that there was a chemical reaction and you would have to balance it appropriately. It does not match the formats of the equations we're looking at here. Okay? So if you think you make an acid, check. Okay? Talk with your instructor about that. Okay? So what we're looking at in a neutralization reaction is we have an acid and a base. These reactions become really, really important, okay, for all chemistry. The idea why? If I look at a reaction and I find an acid, what does that mean? What's it going to react with? A base. What if I find a base? It's going to react with an acid. So if I can determine whether it's an acid or a base, I can actually start to predict products very, very readily. At its simplest level, your neutralization reactions will take some kind of acid. So as a key tip-off, we're going to have a hydrogen. Okay? And we're going to react that with a base. For a general format for our base, we are looking at something that has hydroxide. When we go through and run the reaction, we will produce water, HOH. Why did I write it out as HOH and not as H2O? Does this equation look kind of familiar? Say something like, oh man, that was much further back than I wanted to go. Something like, wow, come on. Something like the double replacement. Your neutralization reactions are double replacement reactions. They are one and the same. Okay? All we're doing is now, instead of saying generic metal ions or generic anions, we must transfer hydrogen and OH. So if we go through and attempt to balance this one, we're going to go through and predict our products. So to start off, we need to get sulfuric acid written out in a formula. First thing that we expect to see, NH, good call. What else we expect to see? Sulfur is probably in there to a certain extent. Why did you say O4? You're absolutely right. It is what it is. You'd have to go back to your nomenclature rules Sulfuric acid is a polyatomic acid or a ternary acid. That's why we don't see the hydro in the name. It's sulfate ion with hydrogen. And we'd have aqueous. Is our formula balanced? Charge on hydrogen? Plus 1, charge on sulfate. Minus 2, does our formula balance? No. What do we need to do? 2 in front, or 2 subscript. Yeah. So formula, subscript. Equation, in front. All right, I know. You got to keep them straight. Now we move to potassium hydroxide. What's our formula for potassium? Formula for hydroxide. Charge on K. Charge on hydroxide. Is it balanced? Yes. Reacts to produce. What do you think? Potassium with sulfate. Why do we put the potassium out front? Our metals always go in front. We always put our cations in front. Okay? Since you said potassium sulfate, let's balance that first. What's the charge on potassium? Plus 1 for potassium. What's our charge on sulfate? Does our charge balance? No. What do we need to do? We need a 2, and it needs to go as a subscript right after the potassium. Okay, you said it, you said it. At least I thought you said it. All right. What else is our product? HOH. Do we have to write it as HOH? No. We're writing it as HOH just to accent the fact that it's a double replacement reaction. What's the phase for potassium sulfate? How do you know it's aqueous? It's got potassium in it. Phase for HOH? Liquid. Is our reaction balanced? Should now be balanced when we put in those 2's. Okay. Hopefully you build enough practice at this that you can very quickly and efficiently see that a reaction is not balanced and that it needs to be balanced, and in theory be able to predict that balancing that swiftly. Okay? Questions about that?
They should have a class with nothing but practice.
It's actually interesting. Different schools do different things. I know when I took chemistry in San Diego,